Our topic for today is similarity of triangles. Now, two triangles being similar is a notion of sameness that is less powerful than congruence. It's going to turn out that all congruent triangles are similar triangles, but not all similar triangles are congruent. However, the notion of similarity is, in fact, a feature unique to Euclidean geometry. Non-Euclidean geometries do not have a theory of similarity, although we're going to have to wait a little bit to see why. Before defining similarity, we need to define a more general relationship between sequences of numbers. So, a bit of notation that we'll use. Two sequences which in theory could be finite or infinite, although for us they will always be finite. Two sequences A, B, C, etc., and A prime, B prime, C prime, etc., are proportional if A prime over A equals B prime over B equals C prime over C, etc. Basically, if all of the elements of the second sequence are constant multiples of the first one with the same multiple in each spot. In this case, we write that the sequence A, B, C, etc. is proportional to the sequence A prime, B prime, C prime, etc. using this tilde notation right here, which is also going to be the notation that we use for similarity of triangles. So that's what it means for two sequences to be proportional. And this allows us to define what it means for two triangles to be similar. So definition 85 says, given triangles ABC and DEF, if 6 conditions are true, then we're going to say that these two triangles are similar. Or, sorry, really they're 4 conditions. If angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F, then, and we have a proportional sequence, or two proportional sequences, if the number AB, the number AC, and the number BC are proportional to the numbers DE, DF, and EF, then we say that the triangles ABC and DEF are similar, and we write that triangle ABC is similar to triangle DEF. Now, the definition of similar that we use here requires a lot. It requires that all of the corresponding angles in the triangles be congruent to one another, and it requires that all of the corresponding sides have lengths that are proportional to one another. Now, some geometry texts will define similarity simply using the angles, and say that just two triangles are similar if the corresponding angles are congruent, and then prove as a theorem that in that case, under that definition of similarity, that the side lengths are proportional to one another. This method of doing things, we're defining similarity to involve all of the angles congruent and the side lengths in proportion to one another. And the first theorem that we're going to have is going to be to show that if you only know the congruences of the angles, well, then you know everything else. The two ways of writing down the theorems and definitions that we use are to a large degree a matter of style, a matter of preference. It is, for instance, my personal preference that the definitions that we use include as much information as possible, include as many of the conditions that we can reasonably want as possible. And the reason for this is that later on down the road, when I'm proving a theorem and I know that two triangles are similar, I like to be able to say, oh, these two triangles are similar. Therefore, by definition 35, these side lengths are proportional to one another. Instead of having to say, these triangles are similar to each other, therefore, by this theorem, the side lengths are proportional to one another. Now, as I say, the differences here are fairly minor and very much a matter of style. So you may see in other treatments of geometry that the definition of similarity has a little bit less to it, but then they include some theorems that sort of go in the opposite direction of some of the theorems that we're going to prove. So let's go ahead and prove one of those theorems. So theorem 86 says, given two triangles ABC and DEF, if angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F, then the triangle ABC is similar to the triangle DEF. This is often known as angle, angle, angle theorem. Now, of course, angle, angle, angle is not a congruence theorem. We can't conclude that the two angles are congruent to each other, but we can conclude that they are proportional. Now, the way that we're going to prove this is by using parallel projection. You'll remember that parallel projections preserve ratios, and the type of construction we're about to do is, in fact, very common when working with similarity, because the parallel projection allows us to essentially prove that certain sequences are proportional to one another. So let's see how this goes. First of all, notice that if a pair of corresponding segments were congruent, if segment AB were congruent to segment DE, then that means that triangle ABC is congruent to triangle DEF by angle side angle. So in particular, the triangle ABC is congruent to the is similar rather to the triangle DEF. If two triangles are congruent, then they are similar fairly trivially, because if you take the ratios of the corresponding sides, then they are always just 1. So if two triangles are congruent, then they are definitely similar. But now we can suppose that segment AB is not congruent to segment DE, and without loss of generality, assume that the segment AB is greater than the segment DE. Now we're going to construct some triangles here. So let's look at how this goes. Let's suppose that these are our two triangles. Let's say that we have A, B, C, D, E, and F. Our hypothesis is that we have congruent angles. Angle A is congruent to angle D. Angle B is congruent to angle E. Angle C is congruent to angle F. And we've assumed that the segment AB is larger than the segment DE. Well, as normal, the thing that we're going to do is we're going to be copying the figure DEF, the triangle DEF, or at least trying to, over to the figure with ABC. So I'm going to put a point G here along the segment AB such that AG is congruent to segment DE, and then we're going to try to construct this this triangle here. Now, we want to take advantage of the fact that we have the parallel postulate and Theorem 76, which tells us about transversals to parallel lines. And so in particular, we're going to be defining this G prime point over here using parallel projection. So let's go ahead and do this. Let's let G be in the segment AB such that the segment AG is congruent to the segment DE. Now, consider the parallel projection from the line AB to the line AC in the direction of the line BC. So we've got our two lines AB and AC, and we can consider the projection from one to the other in the direction of some existing transversal. Well, one transversal to the lines AB and AC is the line BC, and so we can construct this parallel projection. Another way of thinking about it is that we're constructing a line that goes through the point G, which is parallel to the line BC, which is just another way of saying what we're doing. Now, notice under this projection that A goes to just A itself. So we've got this projection which is sending B to C, it's sending G to G prime, and then A gets sent back to A, and that's because that's the point where the two lines AB and AC are intersecting. Let's let G prime be the image of G under this projection. Now, since parallel projection preserves ratios, we have that the distance AB over the distance AG is equal to the distance AC over the distance AG prime. So a parallel projection preserving ratios means that if you take a ratio of distances where all the points involved come from the first line, then you get the exact same ratio if you replace every point there with the point under the projection after you project it. So A gets mapped to A, B goes to C, and G goes to G prime. All right, so now we know that AG is equal to DE. We know that. So the next thing that we want to know is we want to know that AG prime is equal to DF in order to get the ratio that we want. In other words, Or it would suffice to know that the triangle AGG prime was congruent to the triangle DEF. But in fact, we have that. By Theorem 76, the angle AGG prime is congruent to the angle ABC, and that's because the lines GG prime and BC are parallel to one another. But we also know that angle ABC is equal to the angle E. So that means that triangle AGG prime is congruent to triangle DEF by angle side angle. Thus, we have that AG prime is equal to DF. So, rewriting the ratio that we had before, AB over AG equals AC over AG prime, we have that AB over let's see, AG is DE equals AC over, and now AG prime we know is DF. So what we get is we get a proportionality relation between the lines AB, AC, and the distances DE and DF. Now, this isn't quite enough to show that the two triangles are similar, because we also need to show, we're missing that all these also equal BC over EF. So to finish it off, we basically have to note that this argument that we did, showing that we get the side lengths ABAC and DEDF sitting in proportion with one another, we could redo completely by essentially constructing the copy of triangle DEF over in the B corner instead. So let's just sketch out what that would look like. We're not going to have to rewrite the whole problem again, or the whole theory again. We'll be able to do something like the following. Now, if we did something similar, only here we take something like G and G prime there, then we will get a similar relationship where these two sides are congruent, these two sides are congruent. And so continuing the proof, we can say a similar argument exchanging A for or exchanging A to B to C and D to E to F. That is, just write down exactly the same proof, but replace every A with B, every B with C, and every C with A. And similarly for D's, E's, and F's, will show that the segment BC over the segment EF is equal to the segment AC, or the length rather, AB over the length DE. So this, combined with the previous result, which showed that AB over DE equals equals AC over DF shows that we have that AB over DE equals AC over DF, which equals BC over EF. So that means that the sequence AB, AC, BC is proportional to the sequence DE, DF, and EF, and so we have that triangle ABC is similar to triangle DEF. So this shows us that, in fact, it's enough to just know that two triangles have three pairs of corresponding angles, and that shows that, in fact, they are similar, that their sides are also in proportion to one another. Now, an immediate consequence of this is that we don't actually need to know that three pairs of angles are congruent. We just know two pairs of angles. So Theorem 87 we'll often refer to as angle-angle, and in fact we'll use this a whole lot more than Theorem 86. Actually, this is a corollary in the notes. Corollary 87, angle-angle, says given triangle ABC and triangle DEF, if angle A is congruent to angle D and angle B is congruent to angle E, that is, if we have two pairs of congruent angles, then the triangle ABC is similar to the triangle DEF. And the proof of this is simply that the measure of angle C is 180 minus the measure of angle A minus the measure of angle B, which is 180 minus the measure of angle D minus the measure of angle E, which is the measure of angle F. So this shows that angles C and F are also congruent to each other, and then we just use Theorem 86 to say that because all three pairs of angles are congruent to one another, the two triangles are similar. The fact that we can prove that triangles are similar by only comparing two angles to one another is actually very, very helpful, and a lot of what we're going to be doing in the future relies on us just having to look at two angles rather than all three. Now, there are other ways for us to conclude that two triangles are similar. We don't just have to have two pairs of angles to work with. We can also figure it out if we have just one angle and side lengths that are proportional to one another, or two side lengths that are proportional to one another, or if we just have all three side lengths proportional to one another. So these are going to be the side angle side and side similarity theorems. So Theorem 88. So let triangle ABC and triangle DEF be triangles. Part 1, which I call side similarity, says that if we know the condition on side lengths, if we know that the sequence BC is proportional to the sequence DE, DF, and EF, then that means that triangle ABC is similar to triangle DEF. So if we just know the side lengths are not congruent, but proportional to one another, that actually is enough to show that all of the angle measures inside have to be congruent, have to be equal to one another. which is perhaps surprising that um, one of the things this shows is that the proportional side lengths of a triangle completely determine its shape in terms of what angle measures you have inside. And then side angle side similarity says that if angle A is congruent to angle D, and we have a proportional sequence not of all three sides, but just of the two sides that sit on either of either side of the angle A and D. So if we have that the sequence AB, AC is proportional to the sequence DE, DF, then again we have that triangle ABC is similar to triangle DEF. Let's look at the proof. The proof is going to be similar, or the construction is going to be similar to what we had before. So let's look at part one. Let's suppose that we know that all of the side lengths are proportional to one another, and try to prove that they're similar. Now, as we usually do, in this case, the goal is going to be to show that we have two pairs of angles that are congruent to one another, because we want to use the angle-angle theorem, corollary 87. So, we're going to start off very similarly to how we did before. So let G be in the ray AB such that the segment AG is congruent to the segment DE. And then we're going to consider the parallel projection of AB, of the line AB onto the line AC in the direction of BC. And let G be the image, G prime be the image of G under this projection. So we're going to take a line here that's parallel to the line BC. We're going to look at G prime over here. Let's see, we have this congruence already. Now, we have that angle AGG prime is congruent to angle ABC, just like we had before, because we have that the line AB is a transversal of two parallel lines. So by angle, we have that the triangle AGG prime is similar to the triangle ABC. So these two triangles share an angle A, so that's certainly congruent to itself. And because we have these two blue angles being congruent to each other, which comes from the fact that the line GG prime is parallel to the line BC, we have that the two triangles ABC and AGG prime are similar to one another. So that means that we have AG over AB is equal to AG prime over AC, which is equal to GG prime over BC. Also, we have by the hypothesis that AB over DE is equal to AC over DF. Oh, sorry, I actually want these ratios in the other order. we want that DE over AB is equal to DF over AC, which is equal to EF over BC. So let's take these two facts, move to the next page. But remember that we also have that AG is equal to DE. That's how we came up with it in the first place. So also we have that AG is equal to DE. So in fact, all of these ratios are equal. Since the number AG over AB, which is the number DE over AB, appears in both equations. So thus we have that AG prime over AC is equal to DF over AC. So that means that AG prime is equal to DF. And we have that G prime over BC is equal to EF over BC. So G prime equals EF. So we have that AG is congruent to DE. We have that AG prime is congruent to DF. And we have that GG prime, the segment GG prime, is congruent to the segment EF. Hence, triangle AGG prime is congruent to triangle DEF. And since triangle ABC is similar to triangle AGG prime, this shows that triangle ABC is similar to triangle DEF. So if you've got a couple of relations, if you've got one triangle is similar, triangle 1 is similar to triangle 2, and triangle 2 is congruent to triangle 3, then we've got a sort of transitive relationship here where you just take the weakest relation across that whole chain. So because similarity is a weaker relationship, it doesn't say as much as congruence, then that means that the first triangle is similar to the last one. So we have that triangle ABC is similar to triangle AGG prime, and triangle AGG prime is congruent to triangle DEF, and therefore triangle ABC is similar to triangle DEF. Now, the second part, the side angle side similarity theorem, we're not going to go through that. It works very, very similarly, where you're going to construct a copy of the triangle DEF over on ABC, prove that the two triangles that you construct there are similar, and then use the congruence back over to triangle DEF to prove it. You can find details in the notes. Right, so one of the ways that we're going to use the similarity theory of triangles that is a little unique, that you often haven't seen before, is proving the Pythagorean theorem. The Pythagorean theorem, possibly the most well-known theorem in all of mathematics, can be efficiently proved using the theory of similar triangles. Now we've got a couple of things that we need to set up before that, but once we do, then the proof of the Pythagorean theorem becomes fairly elegant. So, first of all, we need some notations or some terminology. Given triangle ABC, the altitude of triangle ABC at A is the line segment AD, where D belongs to the line BC and the line AD is perpendicular to the line BC. So if I've got some triangle here, let's do A, B, C, then the perpendicular, or the altitude of A, would be a line that comes down here, or a segment that comes down here and intersects the line segment BC and is perpendicular to it. Now, we've actually looked at this kind of construction before. We didn't give it a specific name, but it's useful to us now to do it. In this case, we say that the altitude AD, or segment AD, and the side BC are corresponding. So we will often talk about a side and its corresponding altitude, or an altitude and its corresponding side. We've got this. We also know from a previous theorem we know that if the segment BC is a longest side of triangle ABC, then D is in the interior of segment BC, or in other words, it's between the points B and C. When the segment BC is not a longest side of the triangle, then we don't know. The point D, the base of the altitude, may lie in that side, and it may not. All right, so we've got this notion here, and we can use this to prove that when our original triangle is a right triangle, then the altitudes that we get are very closely related to the original. In fact, they give us similar triangles. So this is Theorem 89, and it says, if triangle ABC is a right triangle with a right angle at A, then the altitude of the triangle ABC at A divides the triangle into two triangles that are each similar to the original, or each similar to triangle ABC. All right, so before starting the proof, let's go ahead and sketch out the situation here. So we've got a situation like this. I'm going to try and get us a right triangle here. Close enough. So we've got right triangle here. Right triangle is supposed to be at the point A. And then this is saying that if we look at an altitude, or the altitude of this triangle at A, then the two triangles that we get out of this, ABD and ADC, are each similar to the original triangle. So let's see, proof. So since, or let's start it off with notation. Let's let AD be the altitude at A. Since segment BC is the hypotenuse of triangle ABC, it is the longest side, and so we have that D lies between B and C. So now we've got all these, we've got three separate triangles we're looking at here. The big one, ABC, and the two small ones, ABD and ADC. Now actually showing that we have similar triangles here is going to be pretty straightforward because we have the angle-angle congruence theorem. Or similarity theorem, sorry, not congruence theorem, similarity theorem. So, notice that the angle BAC is congruent to the angle ADB, since both are right angles. Also, we have that angle ABC is congruent to angle ABD, since they are equal. The angle ABC and the angle ABD are exactly the same. So that's enough to show that we've got similar triangles, because that shows that between a couple of triangles we have two pairs of congruent angles. So by angle-angle, we have that one of our triangles, ABC, is similar to triangle. Now, again, here we want to be careful about the order that we write things down in, because when we do say that two triangles are similar, we're actually asserting a particular order that the vertices and angles line up in. The way we make sure that we're doing things in the right order is compare the angles that we know are congruent to each other. So we have that the angle BAC is congruent to the angle ADB. That means that the angle with vertex at A corresponds to the angle with vertex at D. And so A came first in the first triangle, D is going to come first in the second. We also have that the two angles with vertex at B are congruent to one another, and therefore, since B came second in this first notation, A to BC, it's also going to come second in the notation for the other triangle. And so then we were looking at triangle ABC and the triangle with vertices at A, B, and D. So we've got D, we've got B, and therefore we get A. This shows us that the triangle ABD is congruent to, or similar rather, to the triangle at ABC in this particular way. Now, actually keeping track of these things is not too difficult in practice, because you will have a right angle, and the right angles always correspond to each other, of course, and then one of the angles is shared between the smaller angle and the large, or the smaller triangle and the large right triangle. So keeping track of these things in practice is not too hard. In fact, We won't go through the same argument. We'll just write down the similarity on the other triangles. So we've got the triangle ABC, and we want to say that that's similar to the triangle with vertices A, D, and C. So the triangle on the right of the figure. Well, we know that the right angle in the original triangle ABC is at A, and the right triangle, or the right angle in triangle ADC happens at D, so that means that D is going to be there. Also, the two triangles we're looking at, ABC and ADC, share the angle C, and therefore those are going to have to sit in the same position in the notation. And then finally, the only point that's left for the second triangle is the point A, and so that has to go in the middle. All right, so we have that the altitude of a triangle breaks the triangle up into a couple of smaller triangles, each similar to the original. It turns out that this is exactly what's needed to prove the Pythagorean theorem. So, Theorem 90, the Pythagorean theorem. This says that if triangle ABC is a triangle, then triangle ABC is a right triangle with right angle at A, if and only if we have that the side AB squared, or if the length AB squared plus the length AC squared equals the length BC squared. So before we start the proof, let me point out that this if and only if condition is something that we don't always see. We use one direction a lot. We know that if we have a right triangle, then we've got this relationship on the sides that the squares of the lengths of the two shorter sides equals the square of the length of the larger one. But what we don't always use is the fact that if I have some triangle and the sides and the three sides of it happen to lie in this relationship, well, then it turns out that the triangle is a right triangle to begin with. Now, even though not all of us think about it all the time, this has in fact been used by engineers since ancient times, for thousands of years, as a way of checking to see whether a particular structure or building is square, has actually been made to form a 90-degree angle. All right, so let's look at the proof of it, and in fact, we're going to use a very similar figure to what we had before. And in fact, when it comes down to it, this proof is mostly just a matter of untangling some algebra. This is, of course, not the only proof of the Pythagorean theorem. The Pythagorean theorem probably has more proofs than any other theorem ever known. There are hundreds of theorems. They've been compiled, hundreds of proofs. They've been compiled into books. This one that we're using has the advantage that it only uses the notions of similarity of triangles, and in particular, you'll notice that we aren't using any notion of area. We haven't discussed that yet. We're going to do that next. And so our proof here is not going to rely on any idea of areas, which is what many proofs do. All right, so let's let D be the base of the altitude at A, so that we have that D lies between B and C, and we have by theorem by theorem 89, we have that triangle ABC is similar to triangle DBA, and triangle ABC is similar to triangle DAC. This is what we've just proven. Therefore, we can look at the corresponding ratios of sides between these two triangles. Now, there are, of course, 3 different ratios that we can all say are equal. We're only interested in some of them. We're only interested in those ratios that involve side lengths that actually are part of the sides of the original triangle. So in particular, we're not actually interested in the side length AD in this triangle. So from the first similarity, we have that AB over BD is equal to BC over AB. And we have that from the second similarity, we have that AC over CD is equal to BC over AC. So here, just taking corresponding sides here and saying that their ratios are equal. Now, rearranging, we have that AB squared is equal to BC times BD, and we have that AC squared is equal to BC times CD. Therefore, if we take AB squared plus AC squared, let's set that, not set that equal to, but that is equal to BC times BD plus BC times CD. Now, factoring out BC, that gives us BC times BD plus CD, but now we can use the fact that we know that D lies between B and C. So in particular, this BD plus CD expression is exactly equal to the length of BC. And so we get BC squared. Oh, I should have specified at the beginning, we're proving the forwards direction here. So I should have said at the beginning to suppose that triangle ABC is a right triangle, which of course I needed to apply Theorem 89. So we've proven that if we do start with a right triangle, then we get the relationship on the side lengths that we require out of a right triangle. We have the Pythagorean theorem. Let's go the other way now. So now, suppose that we know that AB squared plus AC squared equals BC squared. We're going to try to show that if this is the case, then the triangle ABC has to be a right triangle, and in fact has to have the right angle at A. So to do that, we're going to construct a right triangle with the same side lengths. So let's let D, E, and F be points such that the measure of angle EDF is equal to 90. The segment DE is congruent to the segment AB, and the segment DF is congruent to the segment AC. So we can always do this. We can always construct points like this by the angle and segment construction theorems. So now, this means that triangle DEF is a right triangle. And so, by the first paragraph, we have that EF squared is equal to DE squared plus DF squared. But we've constructed DE and F in such a way that the length DE is the same as the length AB, and the length DF is the same as the length AC. And by our hypothesis, we have that AB squared plus AC squared is equal to BC squared. So that means that EF squared is equal to BC squared. And because everything in sight are positive numbers, we can conclude that hence EF equals BC. So in fact, we get that EF, the segment EF, is congruent to the segment BC. So this means that by side, the triangle ABC is congruent to the triangle DEF. And so in particular, the measure of angle A is equal to the measure of angle D, which is 90. So this means that triangle ABC is a right triangle. So this theorem shows that the conditions of being a right triangle and having the sides and hypotenuse of the triangle sitting in the Pythagorean theorem relationship are completely equivalent. That if you know one, you know the other, and vice versa. Okay, so the Pythagorean theorem is, of course, very useful for a lot of different areas of mathematics, construction. It's been central to all of human civilization. And so it's nice that we have studied it and provided a proof for it based on a very rigorous footing. Now, as I mentioned, we didn't use area here, and that's because we want to make sure that that we have a good notion of area before we start using it. That's going to be our next task. Now, we could, in theory, define an area function in a completely abstract way, like we did for angle measure and distance. We could just provide an axiom that says, let's have an axiom that says there exists an area function that has such and such properties. But it turns out we don't actually need to do that. And the key to defining an area function without introducing any new axioms comes in the next theorem. Theorem 91 tells us that given triangle ABC, the product of any or of the length of any side and its corresponding altitude is constant. Actually, hold on. I want the product of the length of any side and its corresponding altitude is constant. Yes, sorry, I thought I'd messed up that wording somewhere. All right, so what does this say? It says that if we take a triangle, there are several different altitudes that we can take. we could take, for instance, the altitude from B down to AC. We could take the altitude from A up to the line BC, for instance. And we could take, for instance, these two altitudes. And the theorem says that no matter which altitude I take, if I take the length of the altitude and the length of its corresponding side and multiply them together, I always get the same number. Even though the side lengths could be different, the altitudes could be different, or the lengths of the altitudes could be different, the product is always a constant. And therefore, it's a number that we can attach to a triangle in a well-defined way. So let's see the proof of this, which takes a little bit. I realize that I've labeled my triangle differently than how I want to do it in my proof. So let me go ahead and relabel it. So A, B, C, we're going to wind up using these points D and E here. Now, I've drawn E as if it's outside the segment AC. I don't know whether that's actually going to be the case, but I am going to be able to set myself up so that the point D always does lie between B and C as I've sketched it here. So, without loss of generality, we may assume that the segment BC is a longest side of the triangle ABC. So the base D of the altitude at A lies in the segment BC. Then also, let's let E be the base of the altitude at B. We wish to show that if we take the length AD and multiply it by the length BC, that's going to be the same as taking the length BE and multiplying it by the length AC, because that's the product of each altitude with its corresponding side, or the lengths of them. Now, you'll notice that this already looks sort of suspicious. It looks like the sort of thing that we might do using similar triangles. And in fact, what we're going to show, we're going to wind up showing that AD over BE is equal to AC over BC. That's in fact going to be how we do it. Pardon me. All right, so let's consider the triangles ADC and BEC. So we have several triangles that we can look at in this figure, and I want to focus on these two. So the first thing that I want to make sure of is that in these two triangles, the angle at C is the same. Now, in order to do that, I need to know that the point E lies in the ray CA. So we claim that the point E lies in the ray CA and is not C. So let's let's prove this by showing that none of the other possible positions for E can happen. If E actually equals C, this is this is something that would mess up our construction, then that would mean that BC is an altitude of triangle ABC. So that would mean that angle BCA is a right angle. So that means that the hypotenuse of the triangle is the segment AB, and we know that the hypotenuse of a triangle is the longest side. It's the unique longest side. It's longer than either of the others. So in particular, this would tell us that the segment AB, the hypotenuse, is greater than the segment BC, which is a contradiction. All right, so the other possibility is that C is between E and A. So now, suppose that C is between E and A. Let's see. If this is the case, then that means that the angle BCA is an exterior angle to the triangle BCE. Let's sketch out what that position would look like. Now, of course, this is going to look a little silly because we're trying to draw something that can't happen for contradiction. So we're trying to look at the situation where we've got A, B, C, and E over here. But remember that E is supposed to be the base of the altitude from B, and so the segment BE has to be perpendicular to the line AC. So in this case, BCA is an exterior angle to triangle BCE. So that means that since angle BEC is a right angle, that angle BCA is obtuse. So that means that the angle BCA would have to be larger, or I should say why this is obtuse by the exterior angle theorem. But angle BCA is an angle of the right triangle triangle ADC, which is a contradiction. In a right triangle, you have one right angle and two acute angles. So in particular, the angle at C can never be obtuse. So that means that we have that E lies in the ray CA and is not equal to C. Okay, so that means that we can look at some angles that are equal to each other. Now, we have that the angle ADC and angle BEC are right angles, hence congruent. Furthermore, we have that angle ACD is equal to angle ECB, so they are congruent. Therefore, we have that triangle ADC is similar to triangle, so let's see, the angle at D and the angle at E are the right angles, so angle D and the angle at D and the angle at E are congruent to each other, and then we have that the two angles at C are congruent to each other, and so we have that the angle or the triangle ADC is similar to the triangle BEC. Hence, we have that AD over BE equals AC over BC. And this is exactly what we wanted to prove, because if we rearrange it, that gives us that AD times BC is equal to AC times BE. So this shows that if we take a triangle and we look at an altitude, multiply it by the length of an altitude, multiply it by the length of the base, that gives us a constant number. It doesn't matter which altitude we look at and which base we look at. Now, we know from geometry way back, areas of shapes, that we know that the area of a triangle is determined by a base and a height. It's 1/2 times base times height. And so it shouldn't be surprising to us that we do get a constant number out of this, because it's telling us about the area. And in fact, we're going to use this to define the area of triangles and therefore areas of general polygonal regions. Now, it turns out that this is going to take us some work, and so the next section is going to lean heavily into on this result to prove that we can associate a number to a region in a meaningful, consistent, and well-defined way.